Thank you very much for those kind words, and thanks to all of you for coming. I know some of you had to leave work early, some of you had to come a long way from Oban, some people had to come from the city of Edinburgh, so thank you very much for being here. And I'm also aware that not all of you are mathematicians, so I've pitched my talk accordingly. It's slightly dangerous to choose a question as a title because you may then have to answer it. But that would be misleading. I think this question isn't so interesting because of the answer that I might try to give, but because it's shaped research in my own area, mathematical physics, and also in my own research. So the question is a good guide. It takes you to interesting places. And I think that question has done that throughout the history of physics. So I'm going to structure this talk. In fact, historically, it's going to have two guides. One is to reveal the mystery behind this picture that's glimmering in the background, which was on my poster. And that picture has a connection to particles, which I'll explain as we go through the talk. But the other guide is simply the story of our understanding of what a particle is, so a historical route. And so I'll start with a classical picture, a classical particle. And this story begins with the first experimental particle physics facility. It was finished in 1372 in Pisa, at that point still erect, and then designed to incline slowly to be ready for particle physics just in time for this man to come along and carry out his experiments. So Galilei Galilei is perhaps the founder of quantitative physics as we know it, and first developed a theory of how particles move in space. And that theory was perfected and put into a mathematical form by this man here, Isaac Newton, shown in front of the library in Trinity College, and where, of course, he didn't make his great discoveries. He went away and sat under apple trees, or so we're told. So these two together developed the theory of a classical particle, which is probably the picture that you all have in mind when you hear the word particle. It's things like billiard balls, spheres, things that move in space and whose motion we try to describe. That's one of the classical problems of physics, and Galilei himself would have, for example, understood that if you drop a particle straight down or you throw it at some initial horizontal speed, they'll hit the ground at the same time. So you fire a cannonball, flies a lot further than the one you drop, but they'll hit ground at the same time. And Galilei also would have understood that if you play billiard, which you may well have done, the angles that you observe here, the relation is obvious, puzzles between angles, can be understood in quantitative terms. And it was Newton who gave us these wonderful equations that some of you may recognize from school, possibly happy memories. If they're not, don't worry. All I'd like to remind you of that in this mathematical first picture of a particle has no size, it's idealized, it becomes a point. And it's a point that you can put in space. Where you put it in space, you draw an arrow to it that tells you where the particle is. That arrow will now change in time. And how it changes, that's the question that the physicists have to answer. And Newton did this very successfully with the famous equation F is m times a. So that's the differential equation. And he had to invent those symbols here. In fact, he didn't, that was Leibniz, but he had to invent the calculus that's used to write down these equations. So I'm showing you here the notation that, in fact, his competitor, Leibniz, would have introduced. So that's the theory that was developed, and it's now a mathematical task to solve that equation. But for us, the message really is that the first picture of a particle that I think you'll all recognize is that of an object that has a mass, it has no size, it exists for all times. And at a given time t, it's somewhere in space. You can put it somewhere in space. And now I'm going to slip, and occasionally I'll slip in some mathematics. So here, one thing to keep in mind, that mathematically, that idea that a particle exists and you just put it somewhere is reflected by the fact that it's a map into space. The map tells you where you put the particle. Okay, so that's our first model of a particle. It's just a map that tells you where it is. That's all you need to know about the particle. It sounds like an academic model because it talks about point particles, particles that have no size. So let me show you an application of this model. So the most astoundingly successful application of this idea of a point particle is to the Earth. the huge particle that we're sitting on, here viewed from the moon. So this seems paradoxical, that you should be able to apply such an idealist model for something that's so patently not a point. And in fact, it was a worry for Newton, who developed this theory, who wanted to understand mathematically the laws discovered by Kepler that governed the motion of the planets around the Earth. And Newton discovered that he could deduce this by assuming that the planets are points. So he applied the rules I just gave you earlier, that you describe the particle by telling you where it is at time t. And the only thing you had to find in addition was what that force is that you need for this equation I gave you earlier. And he found the force as an inverse square law, famously, so it varies the inverse distance squared between the particles, and it depends on their masses. But with that law, he was able to derive this fantastically beautiful fact that all planets move in ellipses around the sun. And yet he worried. He worried that he had made this obviously stupid assumption that particles are points. So he waited 20 years before he put his theory in writing in the Principia, and he sorted out all kinds of other things. But finally he was able to establish that that's a good assumption. And that's a strange fact, a wonderful fact that we can today prove very easily. So in Newton's theory, it's reasonable to treat huge objects like points, as long as you're only talking about gravitational forces between them. So certainly at that point, this theory of particle physics was seen to be a hugely successful model. You could describe the motion of the planets using it. And so as time went on, people developed a picture of the world in terms of particles. So here we come to my first visit to my poster. And so this picture in the poster, viewed through the eyes of a physicist living sometime in the 1800s, would have consisted of lots of particles. And particles of the sort that I've just given you a picture of, billiard balls, things that we now call molecules. And the only difference between the solid, the liquid, and the gaseous state is how the particles are arranged. If they're densely packed in a symmetrical fashion, which is mirrored, by the way, by the balustrade and the tilings here, then the particles are in a solid state. If they're more widely separated, but still in the collective motion, then you get things like waves, like you can see behind the balustrade. And finally, beyond, if they're moving very far from each other, separately, almost independently, that's what we call a gas. So a very simple picture of the world is just particles arranged in different forms. And the only thing that's really perhaps surprising about this picture, I reckon most of you recognize it from chemistry, physics classes a long time ago, but the thing that I think most people don't take on board is that the number of particles that you need in this theory is incredibly huge. 6 times 10 to the 23 is the number of particles in 22 liters of a gas at room temperature. That's a 6 with 23 zeros. And it's a number so big that it's very hard to get your head around it. But one nice illustration of how big the number of particles is a wonderful coincidence, which is that this is also approximately, give or take 1 or 2 powers of 10, the number of liters in the Earth's atmosphere. And that has an interesting effect. It means if you take a bucket of particles, so a couple of liters of these particles, and you spread them around the Earth, then on average there's 1 or 2 per liter after you've mixed that. And that has striking consequences. It means, for example, that, and this is a sort of standard illustration of this fact, if you take famous people, Caesar, who was killed, and in his last breath ate 2 Brute. So in that 2, he probably exhaled 2 liters. Well, it's a near certainty that one of you will inhale one of the nitrogen molecules exhaled by Caesar during this lecture. Okay? So be aware of that. That's a consequence of the sheer size of this number. Okay? But apart from that, it's particles all around, with one exception, of course. Newton would have liked even the light that we see coming in here and being reflected there to be thought of as particles. Corpuscular theory of light, but that theory wasn't successful. So that idea of Newton's didn't carry the day. And in fact, there's one aspect of this picture which isn't, even in the 1800s, a particle picture. it's the light. So the light was realized by Christian Huygens, and then Thomas Young in an important experiment is a wave. And Thomas Young, with whom I have a connection, because A, he studied in Edinburgh, and B, he was at Emmanuel College, Cambridge, where I also studied. And he proved the nature of light, of the wave nature of light by this very simple experiment. You shine light onto what's called a double slit. And these two narrow slits of light then serve as sources of light, and light travels out in the circular pattern that you see. When that light hits the screen, it will form what's called interference pattern with a big peak in the middle, and then small peaks away from the middle. That interference pattern is the telltale sign of the wave nature of light. And from it, you can deduce what the wavelength is. It's half a micron, or 10 to the minus 7 meters roughly. Again, a very small number. So again, a number that you have to sort of get your head around. It fits into me about as often as I fit to the circumference of the Earth. Okay, so it's a very small thing. But that's the picture. So that's the picture that in the 1800s one would have had of our planet, made up of lots of particles, lots of them, and then there's some waves traveling through them that we interpret as light. So this theory was very successful, and it's a beautiful theory, but it only goes so far. And the new input that one needs to make progress is a thing called field theory. And so now I have to tell you about field theory, and that's hard. Okay, so I had to think of ways of explaining field theory without using any equations, and I struggled. If you look it up in books, it says fields endow space with a property. That doesn't sound so bad. Fields mediate interactions between bodies. That's another thing that you read. So I thought of this illustration of a field theory. So this field theory, the field that I'm talking about here is the field of smell. And we have a field that's being generated by a source here, and it's being received by a sink here. And this field will generate an interaction between the bodies. My guess it's a repulsive interaction in this case, but I'm not sure. So that's the basic idea of field theory. So if this picture, as unpleasant as it may be to look at for a long time, should give you the idea of what a field is. It's no longer a mechanical picture of the universe, but it's objects or bodies generating a property around them to which other properties respond. That's an idea of fields which was fantastically, beautifully developed into a theory of electromagnetism by these two people. The first is Michael Faraday. Many of you may still know him from the 20-pound note, which was taken out of service, I think, in 2001. And the other is the Edinburgh hero, James Clerk Maxwell, who we see here in the statue just outside the Royal Society of Edinburgh on George Street, not holding a pizza cutter, but a colour wheel. And if you have not visited the statue, I encourage you very strongly to do that. You should also have a look at his house, or the house where he was born. This is 14 India Street, where Maxwell was born in 1831. For a long time, that was a building that we used for mathematical physics seminars, and that was a wonderful use of it. It's unfortunately turned out to be too small, so we've moved on. But it's a beautiful building owned by the Maxwell Society, and if you walk by, knock at the door and they'll show you around, hopefully. So Maxwell and Faraday developed a theory of fields, of electromagnetic fields. And they managed to put them, or Maxwell rather, managed to formulate a set of equations that describe electricity and magnetism. So two fields that people knew about. They knew there were charges that repel or attract, and they knew there were magnetic fields, and they knew there were compass needles that respond to magnetic fields. So there was a whole science of electromagnetic phenomena, and Faraday had the intuition to describe it in terms of fields, and Maxwell was able to put the finishing touches on the mathematics behind it. So since Maxwell is personal hero and an Edinburgh hero, these are the four equations that I need to show you in this talk. And I think every Edinburgher should know them. You should know them after 4 pints of lager, and this is how they go. The first equation tells you that charges, electric charges, generate an electric field around them, according to this equation called Gauss's law. The second equation says that there's no similar thing for monopoles, magnetic monopoles. So you can't have an isolated magnetic charge, according to that equation. And you may know that a compass needle is a magnetic dipole. Well, try as hard as you might to cut it into two to get a plus and a minus. It will split again. You get two dipoles. You'll never be able to isolate a single source of magnetic charge. That's what that law says. The third one is Faraday's law of induction, which you're using in a dynamo. If you use a dynamo for cycling and generating light, there's a magnetic flux that's changing to generate an electric field. And the third is one bit which says that currents generate magnetic fields. That's called Ampere's law. And finally, there's one term there that's called Maxwell's displacement current. So you might think he got a lot of credit for having the full 4 equations named after him, when all he did was add a little term at the end. And in some sense, that's correct, but in another sense, it isn't, because that little term makes all the difference. And it's a prime example of mathematical physics at work. And because Maxwell was aware that these equations were not consistent with other laws of physics, mathematically inconsistent. He knew they worked phenomenologically, but he realized they're not mathematically sensible. So he added this term for mathematical reasons, and he gave a new prediction. These 4 equations suddenly predicted there's new things called waves, wave equations of electromagnetic phenomena. And the speed of the waves turned out to be exactly the speed of light, which people knew. So miraculously, from electricity and magnetism, with this little extra term, Maxwell managed to get a theory of light. And the theory of light became part of the theory of electricity and magnetism. It also is the foundation of television, mobile phones, radio, everything we use today. So if I ever need to make a case for the funding of fundamental research in mathematical physics, this is the term that I point to. There's a slightly more obscure aspect of these equations, which, however, is important in this talk. So I need to show it to you, which is we're going to strip these equations of some of the terms that have to do with charges. There's electric charge, there's electric current. If I take this away, they look a bit simpler. So this is electromagnetic theory in the absence of any electric charges. And don't worry, you don't need to solve the equations. But notice one thing. Notice that if I take E and replace it by minus B, these equations will turn into one another. And equally, these equations will turn into one another. E and minus B, that's the minus sign that you need to make that happen. But these equations somehow don't care if I interchange electric and magnetic properties. That's very strange. It's a very surprising feature of these equations, that there's a symmetry that swaps what we call electric with magnetic. Very mysterious, very interesting fact, and one that we'll revisit later. It's called electromagnetic duality. So I think it's time to take a step back. And what is another picture? What is the picture of the world in field theory? It's very different. Now we don't have things that we put in space, but space is endowed with properties. And those properties could be a smell, or there could be an electric field, there could be light. These are things that you don't put in space, they emerge from space as properties. So the field, and if you now watch carefully, is now a map that is a map from space and assigns a property to it. It's not something you put into space. The arrows are reversed at the mathematical level. So the obvious thing would be now to carry on this lecture and say, let's have a field theory of particles. Okay? I mean, after all, this is about particles, so let's try that. And it was tried by another important resident of the Scottish scientific community, William Thomson, or Lord Kelvin. So he was born in Ireland, but he came to Glasgow and was a professor there for a very long time. And he proposed, amongst his many other achievements, proposed a theory of atoms as being arrangements of fields. And the arrangements would be knotted. The idea was that you look at, for example, the hydrogen atom, it's an unknot, it's just a loop. And the more you twist these fields around, the more the further you go up in the periodic table. It's a beautiful idea, and it deserves to be right, but sadly, experiment didn't agree with it. So this theory, on this occasion, the man from Edinburgh was more successful than the man from Glasgow. And this particular idea of Lord Kelvin's was not successful. It's interesting that, so the naming, I was in Glasgow once and gave a seminar, and someone asked me, a physicist, why is the tube station named after a temperature scale in Glasgow? That's a very, very interesting question, because of course you have to sort of untangle the story, which is that there's a river after which the tube station is named, and then there was William Thomson, who became a lord and could pick his name, became Lord Kelvin, who then gave rise to the temperature scale. But those two things, of course, connect that way. So field theory takes us so far, but we have no particle picture at the end of it. So I have to tell you about another theory that's important in this story, the theory of relativity. So now, we haven't thought about time at all, and that's a grave mistake. We have to put time to the picture. And the person who did that was Albert Einstein. So Albert Einstein was the person who taught us to think about space and time together. And by the way, I've not pointed this out, but you may have noticed that I've always put the birth and death dates of the people I'm talking about. And there's a funny coincidence, which is that Galilei died in the year that Newton was born, and Maxwell died in the year that Einstein was born. And the two pairs are kind of matched in interesting ways. I mean, they're kind of part of a team. It's like a relay. You know, one dies and passes the baton to the next. So Einstein took the baton very successfully and started thinking about very simple things in revolutionary terms. And so I invite you to learn relativity in 4 slides. What Einstein told us is that you mustn't just think of space on its own. You've got to combine it with time. And the word for that is called space-time. Okay? So space-time is the picture you should draw when you talk about the world and what happens in it. And then you should organize whatever you talk about in science in terms of events. Okay? An event is this, something that happens here and at a certain time. And so those are 2 events. So this could be, enters in your diary, be in your office at 1 o'clock, go home, 2 o'clock. Events. Okay, so that's not what we do in the math department. But what Einstein pointed out, that if you draw these pictures, you might, from this picture, deduce that these 2 events, so this has just died, the lower of these dots happens before the later dot. So you might think these events are definitely at different times, 1 o'clock, 2 o'clock. But Einstein pointed out that when you change your motion, when you go and you start moving, the notion of simultaneity does no longer apply. So for someone else, those 2 events could lie along an axis of equal time. That means things happening at the same time is not an absolute statement. It depends who is saying it. That's something that Newton and people around him would never have contemplated. Perhaps Newton did. Newton was worried about his naive use of time, but he had no better idea. So he said, time is just, it's God-given. It's what the clock says. But Einstein, and it's interesting, Einstein grew up in Germany, but moved to Switzerland. And Switzerland, at the time, and still, borders with Germany, France, and Italy. And he would have been taking trains, and he would have stood at platforms. But in those days, the timetables of those 4 countries, and even the times, weren't perfectly coordinated. So on a Swiss platform, you would have had different train times for trains from Italy. There would have been 4 clocks, in fact, telling you the times in those 4 different countries. And I think if you, and I'm not saying that's what triggered it, but if you live in that context, you realize, actually, how do we know that things happen at the same time in Rome and Paris? What is the foundation for saying it's happening at the same time? And by pursuing that very simple question, you realize, well, actually, you don't know. And what you need is to specify the frame of reference, and it can happen at the same time or at different times, depending on your frame of reference. So once you take that on board, you realize that the only thing that you can draw is what's called the world line. A particle will trace out, so it's here, 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 will trace out a world line. And that's what you can deal with. And that's what, in relativity, is the language for talking about particles. It's the world line traced out. So it's not just at one time, but the entire history of the particle, where it was and where it's going. There's no restriction other than it has to stay what's called inside the light cone. That means you can't go faster than light. Other than that, you can do anything you like. Any world line is possible. So, in relativity, we have a new set of particle ideas. And the ideas are now that the particle still has no extent. It's a point-like idealization. And in fact, it's quite difficult to go beyond that in relativity. It's quite hard to have a theory of extended things in relativity. So it's still a point. What Einstein added was that the mass of a particle is related to its energy. Famous formula, E is mc squared. A particle still exists for all time, but the mathematics is a world line. And we need to understand the shape of this world line if you do particle physics. So now I'm going to get really ambitious and teach you general relativity. Okay? So general relativity is Einstein's theory of gravity. And you may have heard all kinds of metaphors for explaining Einstein's theory of gravity. A popular one is the waterbed one, where one body shapes the geometry of the waterbed, the other body moves in that geometry, either being attracted or repelled. So bodies change the geometry of space, and other bodies then move in that geometry. That, in one slogan, is the idea of general relativity, Einstein's theory of gravity. Now, here I'm going to use a trick that mathematicians can use. In fact, my head of department may get worried that I'm a physicist, but at this point I'm proving I'm a mathematician by forgetting about the third dimension of space. Let's keep things simple and go into a space that's two-dimensional and one time. Okay? As a mathematician, I can do that. And in that setting, Einstein's very, very difficult theory becomes mathematically tractable. It becomes easier. And in that theory, what happens, so this is my demonstration of general relativity, is if you place the particle at a position here, what it does is it cuts out a piece of space. Space around that particle is now a cone. It's a missing piece. So a particle really suddenly becomes geometry, and that's a very important idea for this talk. And I've drawn it there, so the particle has cut out a piece of space around it, and space is now like a cone. But what that means is that if I draw straight lines on such a cone, they can start going in parallel, they can stay going straight, but they do meet. So particles moving on a cone, even though moving on straight lines all the time, I have to identify carefully so that that's a straight line. See, it's straight. So this is straight, this is straight. And yet they meet. So what that means is that if a particle... yes, there it is. Thank you. That means, summarized in this picture, that a particle is a piece of geometry in this theory. And that's a very powerful, beautiful idea. So it takes us even beyond this field theory idea that particles may be geometry. And the geometry they create tells other particles how to move. That's the sort of new idea for interaction that emerges from Einstein's theory. So, you're still comfortable? Gravity, Einstein theory. So we're going to move on now to quantum theory. Okay? So quantum theory, I've thought about this quite a long time. So quantum theory, I think, can be taught in 3 slides. Quantum theory has 3 important principles, I think, all of which are hard in practice, but not so difficult to state. Oops. Well, actually, let me finish the introduction. So I'll teach you those principles. But quantum theory, unlike the Newton or Maxwell story, is not based around one single person. Quantum theory was developed by a group of people, and I think the image that captures best how it was generated is the image of this house. This is Niels Bohr's house in Copenhagen, the Niels Bohr Institute, and also his family lived there. Niels Bohr, a Danish physicist, who was in some sense the father of quantum mechanics. He was the kind of fatherly figure for a lot of young physicists who invented this new theory of physics at the beginning of the 20th century. And that's the institute that was finished in 1912. Quantum theory sort of reached its final stage in the 1920s. And there's an amazing picture of 1927 when all the inventors of quantum theory met at a conference in Belgium, the Solvay conference of 1927. And you see Albert Einstein sitting here. In fact, every person on this picture is significant and very interesting. But from the point of view of quantum theory, I think the story starts with Max Planck, who invented the constant that determines quantum mechanics. And it probably goes on with Niels Bohr, who developed the first ideas of atomic theory in terms of the quantum language that was emerging. The person who then formulated the new theory and created the first insight into the mathematical structure was one of the young people, Werner Heisenberg. This picture, the person who found the most important and famous equation that governs the whole story is Schrödinger. And finally, the other person I want to highlight, and this is just for lack of time, because all of them deserve a careful discussion, but the final person I'd like to highlight is someone who's probably the least well known, but for my work, the most influential, and that's Paul Dirac, Bristol-born English physicist and Lucchesi professor of mathematics. And we'll come back to his contribution later. But now let me teach you quantum mechanics in 3 slides. So the first principle of quantum mechanics is called the superposition principle. Now this is a strange thing, which means that the world can be in states which are in some sense 2 things at the same time. The famous example of that is Schrödinger's cat, which can be dead or alive, but it could also be I'm giving this lecture or I've already gone to the pub. And in quantum mechanics, you could both of these things could be happening in some sense at the same time. But it's neither and nor or that we can use to describe this. So I've been struggling to find an analogy in one slide, and here it is. It's a picture. And the picture, so can I have a show of hands who sees a young woman in this picture? And who sees an old woman in this picture? Oh, good. So it's 50-50. Now, so once you've seen one, it's quite hard to see the other, right? And in that sense, it mirrors an aspect of quantum theory, which is that this picture is both an old and a young woman. But once you've observed it, it collapses, and it's one or the other, and you can't switch back. So that's one aspect of quantum theory that has remarkable consequences. The other aspect, and that's already hidden in what I just said, is that as you observe it, so there's this bizarre role of observation. Quantum mechanics gives up the idea that things happen objectively and independently of observers, but they bring the observer into the picture and say, all we can say in quantum theory is you can predict the outcome of observations. We give up trying to say what actually happens. You predict the outcome of observations. And as you make the observation, things happen. And again, I had to think of a one-picture description or explanation of that fact. And this is the one that I thought of. So Bugs Bunny doesn't fall until he or she or it observes that there's an abyss. At that point, the experiment carries on. But the observation is crucial. Until the observation is made, nothing happens. Okay? That's what quantum mechanical observations are like. So we had superposition, we had the observation, and the third is that quantum mechanics is probabilistic. Quantum mechanics doesn't, even after all these caveats, doesn't tell you what happens, it tells you only what's likely to happen. And these are pictures of the electron inside the hydrogen atom, but what they tell you is the probability of finding the electron inside the hydrogen atom. It doesn't tell you that is the electron, it just tells you the probability of finding the electron is depicted here. So it's maximal in the center if the electron is in the top left state, and then it has these rather pretty shapes. So these pretty shapes are beautiful, and this, unlike Kelvin's theory, really does work. So this is a very successful theory of atomic physics, in this case only for the simplest of atoms, the hydrogen atom. So what then is a particle in quantum mechanics? Well, it's very hard to pin down. On the one hand, it behaves like a particle. So you can have experiments where I'm back at the double slit. Remember the double slit? So the Thomas Young experiment of the double slit. And if you have particles in quantum mechanics, you can throw them at a double slit and you see exactly what you would expect if you're throwing tennis balls at a gap in a wall. 2 peaks at the back. Okay? That's what quantum mechanical particles do sometimes. But then at other times, they do what Thomas Young observed for the waves. So they behave like waves at other times. Both experiments can be done. They're slightly different observations. The observations make the difference. But both can be observed. So particles in quantum mechanics are really quite tricky to pin down. And Eddington coined this wonderful phrase. They're wavicles. Waves and particles at the same time. Superpositions of the two concepts. But you can see the picture gets murkier here. But before we can come to a modern theory of particles, we need to now combine these various ideas. We need to, actually I'll skip that. We need to combine it with the notion that Einstein had coined. So Dirac, and that's the hero I mentioned earlier, was one who did that first in a very successful version. There's different versions, but this is one version, to combine relativity with quantum theory. And suddenly this particle, this wavicle, this already difficult object, gets more attributes which are interesting and new. Suddenly this particle that started off as a point and at no extent gets a spin. Spin is something that you need to have a size for. A point can't spin. It has to be an extended object. I can spin. And this particle can only spin with a definite, what's called angular momentum, a half or minus a half. That's one outcome of Dirac combining relativity with quantum theory, is that this new property emerges of particles. And the other thing, even more surprising, and one that took him a long time and other people to accept, is that every particle has its antiparticle friend. So this other story of particles living on forever suddenly stops here. Particles can meet their antiparticles, that's their nemesis, and they disappear in a cloud of energy. Particles and antiparticles meet, and the only thing that remains is photons. So this picture is beautiful, but it gets more complicated. The particle doesn't live forever. It can annihilate into energy. It spins. That was Dirac's contribution, and an equation which he described as more intelligent than himself. It's an amazing example of something that you write down and it generates new ideas every time you look at it. Dirac did something else at the same time, which emerges when you combine quantum theory with the theory that Maxwell had invented, or Maxwell had summarized in his 4 equations. Namely, he observed that in quantum mechanics you can violate this law that there's no magnetic charges. Remember this bizarre fact, you can't split a dipole and get 2 magnetic charges. He said that law can be violated in quantum mechanics. And if you do that, at certain points, if you allow that violation, so you insert these magnetic charges, you can explain a very strange fact, which is that all electric charges are multiples of 1 unit. You know, the proton and the electron have the same charge, opposite sign, but they're all multiples of the same unit. There's no reason for that. But if there was one monopole, a single magnetic monopole in the universe, it would explain that fact. Unfortunately, and very unfairly, there isn't a single monopole in the universe. It's one of the very disappointing, so this, Dirac himself loved mathematical beauty and emphasized that in his theory. And this prediction of the magnetic monopole and its study is incredibly influential. There's so many papers, including by people in this room, studying monopoles, and yet not a single monopole has been discovered, and there's overwhelming evidence that they don't exist. But it's a theoretical observation. If there was one, then you could explain why electric charge is quantized. There's another consequence. So another fact of these monopoles is that they are beautiful, but they're not quite perfect. They are what's called mathematically singular, and of course the other defect is that they haven't been observed yet. So there's a structure to this observation of Dirac's, a mathematical consequence. So here, slight apologies to those who haven't studied topology in recent semesters, but there's a interpretation of this theory of electromagnetism where you realize there's a hidden geometry there. I told you about particles being sometimes like geometry in Einstein's theory. Well, in Maxwell's theory, there's also a hidden geometry. It's not quite transparent, but it becomes visible when you look at these monopole solutions. You realize that there's a hidden extra dimension, a circular extra dimension, and it's the geometry of that extra dimension that is related to electromagnetism. And in Dirac's solution, that fact becomes obvious. Becomes obvious when you relate it to a mathematical discovery that was made at the same time. And I hadn't, until I wrote this talk, realized that there is this coincidence between 1931, is when Dirac just speculates about magnetic monopoles in quantum theory, And the mathematical structure is discovered by Heinz Hopf. So this is sort of an aside for those who like these things, as a geometrical picture, a picture of what a magnetic monopole is geometrically. It's a structure of circles twisting over space. Very beautiful interpretation of the magnetic monopole. But let's get back to real physics. So monopoles, beautiful as they are, don't exist. But instead, we have, if we now combine everything that I've mentioned, so quantum theory, special relativity, this electromagnetism, we have to generalize it a little bit into a thing called gauge theory. And we have to add, crucially and importantly, an idea due to Peter Higgs. So we have to add one more ingredient into this picture, and then we get what's called the standard model, which I shall not talk about. I can see that people got worried. But the standard model is hard to explain, but I'm finally back to my picture. The picture of this sky and the sea and the balustrade is now a complicated one with lots of different particles, each of which have this property of having antiparticles and spin a half. But they interact by a set of equations which are very, very complicated. And these complicated equations are such that I think it's impossible to even think of these constituents of matter in terms of this wavical picture that has some spin. The non-linearity in the picture is such that the particle picture is almost impossible to maintain. And that's one reason why the standard model is mathematically, despite its huge physics success, mathematically still not on firm footing. Mathematically, you get $1 million if you solve this. It's one of the prizes. It's mathematically, the standard model is not clarified. Physics, very, very good, but the mathematics behind it is not clear. So it combines all these ideas that I've sketched, but I can't tell you what a particle is in this picture. So therefore, I have to move on to Steve's garden. Solitons. Okay, so we heard earlier that the plaque just behind the Hermiston house where our principal lives, and I cycle by this plaque every morning. So it was very interesting when I've worked on solitons for a long time, and then I got a job at Heriot-Watt, and I cycled to work, and look, right there, as I enter the campus, is a plaque saying the soliton was discovered here. It's like karma. In 1834, so it was an experimental discovery, and so that if our camera pans around, if you go further to the right, there's Hermiston House. And I'll show you a picture of the soliton. So Scott Russell discovered the soliton by accident. He was an engineer who was interested in designing ships and did experiments putting ships through the water. Ship got stuck, and suddenly there was this wave that separated from the bow. And unlike waves that you know that disperse or crash, this one did neither. Instead, it stayed balanced into a perfect shape and traveled along the canal. And at a conference in 1995, colleagues here at Heriot-Watt and visiting scientists recreated it on a piece of the Union Canal. So this is actually on a piece called, is that the Scott Russell Viaduct? Chris, yes. So you can see the little bump of water there, and that bump of water will travel along, never lose its identity, and never change its shape. Remarkable stability. And so this idea, suddenly you think, that's a lump of energy, localized, traveling through space. Particles, surely have to do something with that. And so here's a sort of biographical detail. When I was a PhD student in Cambridge, the author of this book on Einstein, a very, very good book on Einstein, Abraham Pais, came to give a seminar. And he talked in a kind of general, what's called the Sigma Club, philosophical, mathematical physics kind of meeting of people about Einstein's idea on unified field theory. Einstein, as you may know, never accepted quantum mechanics fully, and he developed his own ideas. And Abraham Pais speculated that some of Einstein's ideas on particles would be mirrored in what today, he said, are called solitons. That was a kind of throwaway remark, but it made me go away and find out about solitons. So I started working on solitons, and I got interested in a description of protons and neutrons in terms of solitons. So this is an idea that in some sense harks back to Kelvin, so a field theory of particles. And it looks at first very strange. You get pictures of a proton, which is a ball. The next one up should be a model for the deuteron. Now we're doing nuclear physics. That's a bound state of a proton or a neutron. Complicated bound state, which in standard textbooks doesn't look anything like a donut. So this model would run into trouble if you looked at the classical theory. So the donut, so the deuteron, if you look into textbooks, looks like this. That's a picture from a textbook of the density of matter inside this deuteron-bound states. But what, with collaborators, we managed to show is that if you combine quantum theory with this Skirm picture, you get something that does match. So solitons can be brought into contact with ideas of particle physics, and this is one example where that works. So the Skirm model is one example. There's another one which brings us, let's skip this, brings us back to our friend Peter Higgs. So Peter Higgs, as I said, added one contribution to the standard model, which is a bit like that term that Maxwell added to his set of equations. It makes it all work. It allows you to understand where mass is coming from in the standard model. But his introduction of that field, for mathematicians, that's a field, that particle, also had an unintended consequence. And it's remarkable that this whole literature of mathematics that talks about Higgs fields and as things that Higgs probably wouldn't recognize as Higgs fields. But the remarkable consequence of Higgs' discovery is that you can combine it with something like the standard model to get a particle that describes Dirac's monopole. Remember the story of the monopole that Dirac discovered in quantum theory, but that was singular, mathematically not very nice. Well, if you combine Higgs ideas with the standard model, you get solutions which are solitons, which are smooth, wave-like solutions and have magnetic charge. They're mathematically utterly beautiful. They have attracted vast interest. Constantly people write papers about them, and yet not a single monopole has been discovered. So this is a very interesting sort of account of citations of this paper by a Dutch physicist who discovered the solution. 2,286 citations, that's a vast number of citations in this field. Just below Higgs citations for the paper for which he got the Nobel Prize. Yet Higgs, really, that is physics. This magnetic monopole is not physics, it's just a beautiful idea. It's a bit reminiscent of Einstein's remark on subtle is the Lord, that was the title. And he goes on, but malicious, he's not. This is almost malicious, to put something so beautiful under our nose and then not realize it in nature. But so many of, again, colleagues here and myself have worked on this, been very intrigued by the solution. But I'll wrap up with telling you about one way of combining all these ideas that I've talked about into a new proposal, a very speculative proposal, one that I certainly don't want to compare with the standard model, but one that has attractive features, combines the idea that particles are pieces of geometry. And this is work together with Sir Michael Atiyah and Nick Munton in Cambridge, where we took, first of all, we combined the observation that Maxwell's theory has a hidden geometry in one extra dimension. So I mentioned this, and it's hard to explain, but if you remember, Einstein told us to think of space-time together, so that already takes us to 3 spatial plus 1 time dimension. And there's a way of thinking of electromagnetism as involving a 5-dimensional geometry. So you put this extra dimension, which is a circular dimension, onto the space. In that 5-dimensional space, static particles, whether you take away time, are still 4-dimensional geometries. Okay, so complicated things, but much studied. Then we combined the idea that you can swap around electricity and magnetism. So even though the particle we get looks like it's magnetically charged, we can make it electrically charged by applying this duality idea. And finally, we use the Dirac operator to give us spin. So this combines very beautiful ideas of mathematics to give a new proposal for thinking about elementary particles like the electron and like the proton. Very, very ambitious and in its early stages. But we've got some funding to explore it, so I've got EPSIC funding with a postdoc, Guido von Ketty, and a PhD student, Rogelio Jante, working on this. And since there's university management here, there's impact of this already this is blue sky adventurous research, but it's very, very interesting that these ideas, which are abstract, beautiful mathematical concepts, the soliton, the gauge field, the monopole, are increasingly being realized in the laboratory in solid state or atomic physics setups. It's a bit reminiscent of what Daniele talked about, the analog black hole, which the black hole is a very difficult solution in Einstein's theory of relativity, and yet these days we are able to recreate them in analog situations in the lab. So a similar thing is happening with these non-abelian solitons, Dirac fields. Even though they come out of very mathematical research, they're now finding their way into everyday physics. So, impact tomorrow, I don't know. The short-term impact, there's the interaction with those people creating these things in the lab. And finally, I have to tell you where this picture was taken. So I'm going to zoom back from where this picture was taken, and zoom back further. The camera pans round. There's a tropical landscape with the sun setting. And if you walked into the village in the distance, people will tell you that you are in Ghana, in the village of Biriwa. And if you then turned round and took a picture of where the picture was taken from, you would see that there's a building on the top of the hill with balustrades in blue and white, like the one through which I took the picture, called the African Institute for Mathematical Sciences. And Steve introduced that project, which is to train graduate students in mathematics across Africa, in institutes across Africa. I got involved with this quite early, and Harriet Watt University has been very active in supporting it. So here's a picture of Neil Turok receiving the honorary doctorate at Harriet Watt in 2012. And you can see the title there, the Next Einstein Initiative. So the idea that we're looking for the next Einstein in mathematical research across Africa. And it's interesting, so this is a picture, this is a screenshot I took of the web page of the Next Einstein Initiative, which itself had taken a screenshot of the Harriet Watt web page that showed the picture. Now we're being filmed, and it's possible that the people at this could go on for quite some time. This is again a picture of from the same web page of some of the students from those centres who have come to Scotland for their PhDs, and in the middle is the director of this initiative meeting some of the students. So at the end of this talk, what is a particle? I can't help noticing that what got me onto this track of thinking about particles was a throwaway remark about Einstein at a seminar when I was an innocent young PhD student. And now I give this talk, there's again a Next Einstein Initiative that I've ended up involved with. So I think someone is having a laugh. Thank you very much.